let's just do a quickie review. I mean, what we did last time, we gauged Lorentz transformations, basically. We have, x prime mu is lambda mu nu of x nu, but we now made this thing of x, and we made this infinitesimal, so that's a function, local function. There was an immediate success that we got out. When we did this, we promoted g mu nu into a field, and when we wrote a covariant action, for a scalar, the Lagrangian being, so it's the action being d for x square root of minus g. There's 1/2 g mu nu of x d mu phi d nu phi minus m squared phi squared. So this is now invariant under this local Lorentz transformation, and it was sort of constructed that way. But we got an immediate success. We got the variation of the action with respect to g mu nu gave us the energy momentum tensor, and the exact relation it's 2 over root g is the energy momentum tensor. So there's our source. That's what we wanted all along. And just a sec. Okay. So we got what we wanted there, and now we're working on constructing the action for the general relativity side, the gravitational side. And for that, we got the covariant derivative. So we imagine a vector field V. Let's see. Yeah, it's V prime beta that transforms the same way, V beta alpha, V beta, V alpha, where this is the same lambda of x. So that's the local transformation there. We insisted that we have a covariant derivative such that d prime mu v beta, v prime beta transforms covariantly. So lambda lambda d v. And then I'll fill in all the boring indices. There's a lot of boring indices here, but mu nu beta alpha. Hi guys, I'll make a quick review in a second. Okay, so that the covariant derivative transforms that way. So guys, up in Dartmouth, I started off just by starting a review talking about how we got a covariant action whose variation was T mu nu, and I'm reviewing the construction of the covariant derivative now. Okay, so the covariant derivative transforming like that, and you basically just fill in the indices, but dv prime is lambda lambda dv. Okay, that's what it means to be covariant. Requires that if I take d mu v beta is d mu v beta plus something gamma mu nu beta v nu. So this is the new piece that you have to add to make the covariant derivative. We had gamma prime mu nu. I have lambda here, so let me just keep the notes the way they are. So there's a lambda, 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 gamma, and an extra piece. I'll fill in the indices, lambda, d mu lambda. Okay, schematically, that's all you need to know. Okay, that it transforms covariantly plus an extra piece. But let's fill in the indices here. So the mu, nu, and lambda indices go first there. Then let's make rho, sigma, and I have eta. That's the second indices there. So this becomes rho, sigma, eta. And this becomes, let's see, this, what I wrote is mu is actually d rho. The indices here are eta, alpha, alpha, sigma. There we go. Okay. Conceptually, you don't have to worry about it. I mean, clearly, to get everything right, you need to know what the indices are. Now it's an alpha up there. And I stated, but did not derive, I'll derive it today, that gamma mu nu lambda is 1/2 g lambda sigma d mu g nu sigma plus d nu g mu sigma, so symmetric in mu and nu, minus d sigma g mu nu, again symmetric in mu and nu. Okay, so there we go. Does anybody have questions about that stuff? Okay. What I need to do is, what I want to do is I want to go through a quickie derivation of that, because it actually tells you something. It tells us two things. And first I also then want to do tensors in general. So tensors are things that transform like they transform covariantly. Okay, which means that if I have some tensor with some couple indices upstairs, let's say alpha, beta, and gamma, sigma downstairs, and maybe there's more of these guys floating around, that transforms as lambda, 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 t. Oh, let's make it, so it's alpha upstairs, I'll make it alpha prime, beta upstairs, beta prime, gamma, gamma prime, sigma, sigma prime, and then this is alpha prime, beta prime, gamma prime, sigma prime. Okay, so basically just all the indices transform the right way, with this thing being lambda of x. Okay, the covariant derivative that we constructed, if I have d mu on a tensor with two indices, let's make them both upstairs, alpha, beta. That's just the usual derivative, t alpha beta. And then there's gamma term, gamma t. Is there a question there in Dartmouth?
No.
Okay. There's the gamma terms that are connected up to these tensor indices there. So one of them is going to be mu nu alpha t nu beta. And the other one will be the beta index. So mu nu beta t alpha nu. Okay, so basically you just work on each index just like we did up on the vector there, okay? When the indices are down, there's just a slight change. So if you have d mu acting on t, well, I'll just do some vector downstairs. Vector downstairs, vector lambda downstairs. It's the usual derivative. Then it's minus gamma mu lambda sigma v sigma. There's a minus sign associated with this, and it comes from this. Okay. If I have v lambda, that transforms just like a scalar. So the covariant derivative here is the same as just the usual derivative. So you just use usual derivatives because there's no need for any of these gammas. But then if we know how the upper transforms, the lower transforms in a particular way also, and that's where the minus sign comes from. Same gamma, just the minus sign. So that's where you get that transformation law from. So you just, when you have tensor with things down, you just use this as the property. Okay. So there are a couple things to say here. One is specific to general relativity. Gamma mu nu lambda is not a tensor by this definition. Okay. Look up here how it transforms. It transforms. There's the covariant piece, is sitting right there, and then there's a gauge piece in addition. So it doesn't transform just simply, it transforms into something. Okay, so this guy is a connection, is phrasing, or the affine connection. But in general, it transforms differently. It transforms like a tensor plus a gauged piece. Okay. Now, just for fun, this is now an aside. This is something from gauge theory that's not that well known. That the photon is not a 4-vector. Under usual Lorentz transformation. So now we're not doing general relativity, I'm just doing gauge theory. So normally we do a mu of x, and that sure looks like a 4-vector, right? It's got an index mu on it. We dot it in the usual ways. And we expand this d3p 2 pi cubed 1 over square root of 2e. Then we do epsilon mu of p lambda and a dagger of p. No, that's a of p and lambda there. E to the minus I p dot x plus Hermitian conjugate. You get the opposite piece there. So this is how we describe a 4-vector, and this guy satisfies p mu epsilon mu equals 0 to get the to describe just the transverse degrees of freedom. And in fact, if you have a free field, you can also actually set epsilon 0 equals to 0. So that the epsilon, if you're moving along the z direction, is 1 over the square root of 2, 0, 1 plus or minus I, 0. Those are the transverse degrees of freedom, right? But if you do a Lorentz transformation, I'm sorry, was there a question? No, all right. The Lorentz transformation would be, lambda mu nu a nu, which implies lambda mu nu epsilon mu nu. And this is not, so this is my epsilon prime, but this guy no longer in general satisfies. No longer satisfies, the p prime dot epsilon prime equals 0. Okay, and the easiest way to just mentally do this calculation is just boost it perpendicular to the direction of motion. Okay, then you know that the Lorentz transformation picks up a time component because, p, the time component shift. There's going to be now a piece that sits in the time part of the vector there. And so it's no longer going to have that form. Then to do a Lorentz transformation, a gauge transformation to put it back into the form. Okay, so I don't mean to go too far down this pathway, but photons by themselves are not Lorentz for vectors, but if you supplement by a gauge transformation, the offending pieces can be removed. The place to read this is Weinberg's. It's the only place I know. QFT, Volume 1, Chapter 5.9. So if you didn't be interested in seeing that, it lives in that chapter and actually has some interesting implications sometimes.
Hey, John.
Yes?
Question.
Yes.
Okay, you need to do the gauge transformation because what you're working with is the vector potential.
Yes.
Why not just expand out the field tensor in Fourier modes instead of the vector potential?
Well, yeah, okay. So the question, let me repeat for the class here, is that the trouble came because I was expanding up the vector potential. Why not expand the Fourier modes of the field strength tensor? And so whoever asked the question is absolutely right. F mu nu is a Lorentz tensor. And so, and has none of these issues. So it behaves properly under Lorentz transformations. And so E's and B's behave properly, and all that's nice. I'd say my answer to the reason why you deal with the gauge potential is that the Lagrangian has a piece in it which is minus a mu, j mu.
So it's
and
just
covariant derivatives have that also. I don't know. Is that not a good answer for you?
No, that's fine. There's no other way to construct interaction with the field tensor instead of with the gauge potential.
Right.
Okay.
So if you're doing a Lagrangian, you're sort of stuck with the gauge potential. but in some ways, the fact that the connection is not a tensor also has some of the same flavors. It transforms as a gauge with a gauge transformation plus. Anyway, that was an aside. Okay, we ready to go on from the aside? All right. So here's the place I want to derive gamma. And the topic, though, goes under the name of metricity. So this goes back to the equivalence principle. Remember, we saw there that if you were in free fall, there's no gravitational force, locally anyhow. And so this let us say that there's coordinates such that G mu nu in these coordinates can go into the eta mu nu. Okay, and we also use the equivalence principle to set up coordinates so you imagine doing, sending out light beams and stuff like that to map out little coordinates locally. So, well, we have to worry about our coordinates in general. We can always define them to be locally flat. So the basic point of that was that we can take G mu nu goes to eta mu nu by some choice of coordinates. The deviations also can be set equal to 0. So remember, gamma is the first derivatives. These guys can also be set to 0 in this coordinate frame, so that you can choose coordinates where that works. If that's the case, let me just take it to be the case for the moment, that you then get the covariant derivative on G mu nu is equal to 0. So you're both locally flat and your first derivatives vanish. Okay, second derivatives actually don't vanish. Okay. So you might, I might try to come up with a better argument for why first derivatives vanish. Pictorially, for me, I like the fact that I can set up the deviations being quadratic. There's a more physicsy derivation if you want, and I don't want to go through it, but here's what it is. If you do a point particle and see how a point particle moves. If you do a point particle, the equations of motion of a point particle are x double dot mu, so the second derivative, the acceleration, plus this connection. Let's say I need lambda sigma mu x dot lambda x dot sigma equals 0. So this is, if you go to any GR book, this is the geodesic equation. It's how a point particle moves. And so this is the acceleration, and this is basically the force over the mass. And x dot actually is the proper time. Okay, so all these little things you see in any GR text. But the basic point here is that we know that we can choose a frame where the particle doesn't accelerate by just choosing your coordinates right. In those coordinates, gamma equals 0. So I get gamma is equal to 0, G is equal to eta in these coordinates, and therefore I get this metricity condition. Okay. This is true in all metric spaces. So that's why the phrase. So we're just going to take this as a consequence of the equivalence principle and our use of metrics. Okay. It's a pretty useful thing, so it's worth emphasizing by itself. But here's its utility for us. The derivation here now. I actually won't do all the steps, but it's pretty easy. You do the following. You say d mu, let's see, get my notes. D alpha g mu nu is d alpha g mu nu plus, now minus gamma g minus gamma g, and let's fill in the indices. So alpha alpha mu sigma, then I want sigma nu, and alpha nu sigma mu sigma. This is going to be equal to 0. So you're right, this is 1, 2. I do permutations on this. D mu g nu alpha is d mu g nu alpha minus gamma equals 0, gamma g. You can fill in the things in the 3. You do d nu g alpha mu
That's a mu.
Okay, so let's not fill in all the equations, but you can do it. It's thing. Then we choose gamma mu nu sigma is to be symmetric. Gamma nu mu sigma. Again, that's a choice at this stage. We'll relax it later, and I'll say the code phrase is torsion when I relax it, but let's keep it now. Okay, if you do that, then you take 1/2 of 1 minus 1/2 of 2 plus 3, and that turns into the equation of gamma mu nu sigma g sigma alpha is this. Well, I've got 1/2. It's just the derivatives. I've isolated gamma out. 1/2 g. Well, let me actually not bother writing it out. I basically get the formula from before. Okay, so the way to derive what gamma is just to use this definition and metricity, and and symmetry, and that fixes it. Okay, so then the other way to do it was just to plug away, taking different combinations. You could get it to work. Okay. So done with driving the connection. We set to get to the curvatures. Okay, so I'm heading, oh, come on. There we go. I'm heading towards the definition of curvatures. And remember when we did Yang-Mills theory, we had, at that stage, we had d mu on psi is d mu plus ig some lambda dot a over 2. Let's put indices on this guy acting on psi. We took this transformed as d prime mu is u d mu u dagger, and this is the same thing that we had above here. D prime mu psi prime is u d mu psi. So it basically transforms just like any element in the group. Psi goes to u psi, d prime u goes to u d psi. So because we had this transformation property here, we knew that if we took d mu and commuted it d nu acting on psi, we just got I g over 2 lambda a f mu nu acting on psi. And f mu nu was d mu a nu minus d nu a mu minus g a mu a nu. And actually this is this matrix notation that I started using back then. Those guys are all matrices. This a with a double bar under it is lambda a over 2 a. Okay, so it basically is notation for usual derivatives and then a quadratic piece. Okay, so let's do the same thing. So here, let's try the same thing. Let's take d mu and d nu acting on some v beta. That's some vector. Okay, we know how that transforms now because we know how d transforms. And we know what these derivatives are, and we know how to act on them. Okay, so now there's a little bit of a tensor calculation. Let's define the product here to be r mu nu alpha beta upstairs there v alpha. Okay. Well, you can see a couple of things that you have here. You have the usual derivative acting on the gamma. So there's a gamma inside the d here. And then there's pieces with two gammas. Okay. So let's not do all the algebra. Let's write it out. R mu nu alpha beta, okay, is the derivative mu acting on the gamma nu alpha beta. That's pretty obvious. Remember when this derivative acted on v, I had that gamma alpha beta piece that was sitting there. And then there's the reverse combination that's also pretty obvious. It's anti-symmetric in mu and nu. So, okay, so those are obvious. The last one you have to work a little bit to get the right tensor combinations. It's gamma mu rho beta gamma nu alpha rho. And then anti-symmetric in mu and mu nu rho beta gamma mu alpha rho. Okay. So the analogy is supposed to be up there to the F mu nu. This is the equivalent of F mu nu. It has derivatives of this connection. And connection was the thing that transformed like a gauge field. And by construction, since each of these derivatives transform covariantly, this guy is a tensor. In other words, it transforms covariantly by construction. Okay. I'll give you the properties in a minute, but let's just define two other things. So this is the Riemann curvature. It's the equivalent of the field strength tensor. Two extra indices on it because we're doing gravity, which is, well, there's only one extra index. F mu nu has an index A. Now we've got one extra index. Instead of A, we've got mu nu. When we do this for fermions, it's going to actually look even closer, but to the usual field strength tensors. But then we can do the following. So we've got this defined this way. We'll define a two-index guy, R, let's make it nu alpha, by summing over the two of the indices. It's the following. It's R, my convention are nu alpha, mu. You sum over the upper and one of the lower indices. And you could have used the second index. The second index is just anti-symmetric, so there's minus signs associated with conventions on which indices you sum over. You couldn't use the third index. It's I don't have the proof for you right now, but if I take mu nu alpha and sum over that one, that equals 0. And I'll give you some of the properties of this thing in the end. I'm sure I can come up with a good derivation of that, but I don't have it on me. Okay, this goes by the name of Ricci. Ricci curvature, and you can take one more. You can take G nu alpha R nu alpha equals R, which is the Ricci scalar. Okay, these guys are also tensors. The first guy was a tensor, so contracted indices keep it a tensor. And the G mu nu keeps it a tensor. So these guys are tensors. This guy is a scalar. In other words, it doesn't change under coordinate transformations. And that by itself is an amazing construction now. If you had just set out to derivatives of G, that it's a scalar, it's a painful exercise. But by going through this covariant derivative trick, it's pretty easy. Okay. The thing that's important to note is that this is like two derivatives in G. So because there's either derivatives on the connection, but the connection already has one derivative, or it's two connections. Each connection has one derivative. So when we're doing wave equations and the like, this is something that has two derivatives of G on it. And so it's a good these guys, all these curvatures are good candidates for wave equations, because we normally have wave equations box function equals something. So that's good. That's also a success in a way. We're starting to get the wave equations out. Okay, so just looking ahead, we're going to do it today. So, but this guy being a scalar makes a good candidate for the action. So the action will be proportional to d4xr. And so our goal at some stage today will be to vary r and get the equations of motion. Okay. We've already varied the matter side, so we're going to get things that look like, just schematically, r mu nu goes like equals something times t mu nu. This is varying the gravitational side. This is varying the matter side, and so that's where we're headed. This will be something that looks in the end like box G. Schematic. Yes.
Are you always going to assume that there's no torsion, that the connection is symmetric?
I'm going to drop that in a later section. So okay. My plan is to do GR up through the quantization of general relativity and use effective field theory, and then come back and do fermions and torsion and Holtz terms and things like that as a separate unit later on.
All right.
Okay. I know I can hardly wait. I need to learn some of that stuff too. Okay. Now fermions are a slight bit different in this case. Okay. Before I do this, so this is just to keep you motivated to slog through this next little bit here, which are the properties of the Riemann tensor. Okay, I have to do these guys. Okay, so from the definition, we have an easy one. So we have R mu nu alpha beta. This is from the definition. We did it from the commutator, so it's minus R nu mu alpha beta. So it's antisymmetric in the first two indices. Okay, that's obvious. Notation-wise, here, let's do some notation. This is R mu nu in square brackets alpha beta. When I put it in square brackets, means 1/2 mu nu minus the nu mu. So the antisymmetric combination with a half in there. Okay, and I shouldn't use. So let's put it in like that. So it means you take the antisymmetric combination of the indices. if you, I'm also going to use the notation soon. If I put it in round brackets, mu nu, it's 1/2 mu nu plus nu mu. Okay, so anti-symmetric and symmetric combinations are the brackets there. Okay, so now if you lower, if I put all the indices down, r mu nu alpha beta as r mu nu alpha gamma g beta gamma, so I lower the index using g. Then through some work, again, I'm not going to do this work, mu nu alpha beta is r alpha beta mu nu. So it's symmetric in the block, the first two blocks and the second two blocks. That implies then, if that's true, then it's also symmetric in alpha beta when they're down below. So that then says r mu nu alpha beta is r mu nu antisymmetric in alpha and beta. And since it's antisymmetric in mu nu alpha beta, okay. Less obviously, but true, at least, is r mu nu alpha beta. If you take the antisymmetric combination of all those initial indices, that's equal to 0. This is only true if gamma is symmetric. So that falls apart with this torsion business. This is one of the Bianchi identities. I'm not. No, that's right. Sorry. Yes, you're right. Just if it's symmetric. I was going to write it with the antisymmetric combination there, or the way I was trying to write it is gamma antisymmetric is 0. That's the equivalent. Okay. So that's an identity. I don't know, and more, even less. If I take d lambda r mu nu alpha beta and I antisymmetrize the first three, that actually goes with 1/3 factorial there. This is, yeah, so a lot of combinations there. If I antisymmetrize that, that's equal to 0. There's a lot of algebra to prove with that. Leave it. That's another Bianchi identity. If you contract, from at this stage it's not so bad, you contract an index on the R's here. You take, I don't know, let's see, how much do I want to write out? Let me just say that if I contract indices up there to form scalar curvatures, I get the following identity. So it's basically definition of the contracted Ricci scalars plus Bianchi 2. I get 2 d nu. It's supposed to be an r sitting there. R mu nu. So I've raised one of the indices there. Equals d mu r. Okay, so that's a useful one. And in particular, this implies the following. D nu of r mu nu minus 1/2 delta mu. Let's see, nu is upstairs, mu is downstairs, r equals 0. So this is contracted Bianchi identity. Or often just said Bianchi identity. Okay, and its beauty is that this guy here is going to be the Einstein tensor G mu nu, and so this Einstein tensor is going to be conserved. Okay, so there's, but the conservation law, I mean, you can sort of just trying to see the steps that go into this. There's just a bunch of algebra and the definitions of all these guys. All right. Okay. So now we can wake up because we do some real physics, get the Einstein equations out. All right, our starting point is an invariant action. We have an invariant, so the action we're going to use is what we've got already, that curvature. This is the Einstein Hilbert action. We're going to derive it from an action principle, and so it has an integral d for x square root of g. That's the invariant volume element. Then we have the curvature, and we give a coefficient in front of it, minus 2 over kappa squared. Okay? This, we'll see. We have to turn this into show that this is gravity, but kappa squared is going to turn into 32 pi g Newton. Okay, this comes later. But for now, we're just carrying around the minus 2 over kappa squared. And again, when you're reading other books or reading any book, since I am not a book here, that minus 2 could be plus 2 in some conventions, and because we remember we had some choice on which ones we contracted to form the Ricci scalar, and we have some choices in the definition of the metric and the definition of the curvature. All those things are choices that we had.
So you really mean square root of negative g, right?
Minus g, yes. Yeah. So the square root is, the question was, do I mean minus g? And I do mean minus g. And it suddenly appeared there. What do you know? Okay, it's my own personal habit to know that it's minus g and just write square root of g when I'm making my own notes. So you will catch me on this again and again in the future. Okay, so we want to vary this and get an equation. So, I mean, well, first of all, this is an accomplishment by itself. We now write out the whole action. And we've made it generally covariant. So, but to complete our mission, our assigned mission is to vary this. And so I have this constant is just going to be carried in the front. I have integral d for x. And basically then I have to vary square root of g, g mu nu, r mu nu. Okay, we're going to vary each of these guys. Well, so this is going to be then equals 2 over kappa squared integral d for x. I've got delta the square root of minus g times r left over. I then have the square root of minus g delta g mu nu and r mu nu left over, and then I've got the square root of minus g mu nu, and I'm going to vary r mu nu. Okay. The first of these we sort of have done, kappa squared integral d for x. I can pull out the square root of minus g out here. The variation of the determinant of square root of the determinant of minus g is something I did before. Hopefully I did it correct. It gives minus a half g mu nu, and let's put, I want that lowered, sorry, don't copy yet, g mu nu lower and vary delta g mu nu upper. Okay, the 1/2 clearly comes from the square root. The minus comes from the minus. The g mu nu, delta g mu nu comes from varying the determinant. Okay. The second one is trivial. I've got delta g. I've pulled it outside, so I've got just r mu nu. And then the last piece takes a little work, but I'm just going to tell you that and then show you, or show you at least some of the algebra associated with it. This is going to be a total derivative. Okay. So I'm going to come back and do the delta r mu nu and argue that it's a total derivative in just a second. But once you get this, this is then the equations of motion. So this is then equal to 2 over kappa squared integral d for x times g mu nu, which is going to be the notation for the Einstein tensor delta G mu nu. G mu nu is R mu nu minus 1/2 G mu nu R. And I've still got the square root of minus G. Thank you. Okay. So there's our variation that's going to be of use. And then I just have to complete the proof. I have to do the total derivative argument. So here's how it goes. If you take delta R mu nu, so R mu nu is made up of delta. So this is d lambda. I've contracted this gamma mu nu lambda plus gamma. All right, lambda rho lambda gamma mu nu rho minus lambda exchanged to mu. So it basically, no, actually that doesn't make sense. It doesn't make sense. Then I'm sorry on this. What can it be? It's because mu is not summed over and lambda is, so I can't do mu goes to nu. So I'm sorry, I have clearly a mistake in my notes, but here's the argument anyhow, and maybe it'll be obvious. So a covariant derivative, and so basically I take I take the derivative on delta gamma mu nu lambda, and then there's two terms here. It's delta gamma lambda rho lambda. So that's gamma plus the other one. All right, so minus whatever that minus sign is, whatever my mistake was. And the covariant derivatives, d lambda of delta gamma mu nu lambda is this derivative lambda plus, again, there's too much copying here. There's a gamma piece, a gamma delta pieces. There's a sum of these delta gamma pieces. All right. I'm going to give up on all the algebra, but the end result is the delta R mu nu is the derivative lambda on delta gamma lambda mu nu. You can see that developing just starting from there, and then it's minus the derivative mu on delta gamma lambda lambda nu. So again, it's just a bunch of algebra pushing these indices around, and you can start seeing it develop from that piece there. But then if you take square root of g mu nu integral d for x, a derivative a covariant derivative on delta from delta gamma, that's a surface term which, if you take it out to infinity, you drop it, or you hold delta gamma fixed on the boundaries, because the covariant derivative, when I integrate by parts on the square root of minus g mu nu gives 0.
Wait,
Okay.
John,
Yes.
do you get a total derivative for that piece only if you assume metric compatibility?
Yes.
Okay, or could you do it the other way around then, and like, what is it, the Palatini formalism,
Yeah.
and vary with respect to the connection, and then derive metric compatibility?
Yeah. Yeah. So actually, next time I actually are going to say a little bit about first order formulation there. The question was, well, actually, let me postpone the question for the audience here. The question is, there's also a first order or Palatini formulation that you can use to derive the metricity condition. Here I'm doing it in reverse. I've assumed this, and therefore my covariant derivatives on the other side, on these other guys, give 0, so it's a total derivative. Okay. So I've gone this direction. I will do this Palatini formulation. This is actually has a name. This is the contracted Palatini identity. I'm not an expert on this. I've seen this said. But for the scholars among you, there it is. Okay. So if we add the matter side in, again, I'm hoping for a minus sign come out correctly. Otherwise, I will correct this if I have it wrong. We take S total is the Einstein Hilbert plus S of the matter side. So it would be something like, d4x minus 2 over kappa squared r plus, and I've got my square root of minus g there, g mu nu, d mu phi, d nu phi, etc. We take the I have a minus sign trouble, which I will correct next time. We take delta action, delta of the matter part, g mu nu, is two over the square root of g minus g t mu nu. We vary what we just had up above. The Einstein equation, which I hopefully with the right sign, I don't know, r mu nu minus 1/2 g mu nu r equals. All right, so there's a 2 there. There's a 2 sitting here. Turns into kappa squared over 4 t mu nu. And so there's our Einstein equation. Remember, kappa squared was 32 pi squared, so this is 8 pi g Newton is kappa squared over 4 when we come there. Okay. Actually, that took longer than I thought, but I'm just going to stop there. but we've got it. Okay, we've got general relativity at this stage from an action principle. Okay, so next time I actually have a bunch of little things to do. I will do things like the cosmological constant and the Palatini forms and some more stuff on mu. Actually, why don't I do the following in the remaining time? Here's an exercise. Let's do hand out an exercise if you want to do it. Let's do the following. Let's take the following metrics, spatially a metric that has no time component, no spatial component variation. dt squared, but it has time dependence, and a squared of t dx squared. So g has f and t in it. Okay, the exercise is to show that r is 6 over a squared f cubed, and what is it? It's f a dot squared plus a double dot minus a dot f dot. You then write the matter Lagrangian as a function of phi f and a. You vary the action f, and you vary with respect to a. If you do this, this is the Friedmann-Robertson-Walker equation. Friedmann-Lemaitre, Robertson-Walker. And this is the time component. This is the space component. So this is the equations of motion for cosmology. You get it by assuming this form, varying the functions. The forms that you normally see in the end are set with f equals to 1. That's a gauge choice. And then a of t varies. But there's another choice that you sometimes see, which is f equals a, a conformal choice. Okay. So you can get Friedmann-Robertson-Walker in either of these two bases by starting from that action. Okay, anyway, so let me stop.